My name is Pavel Emelyanov. I work for Virtuozzo company. And first of all, a few words why Virtuozzo on the NGINX conference at all. So Virtuozzo is a platform which allows people to start so-called light virtual machines. We used to call these light VMs containers, which reflected the fact that this virtualization is not hardware level but operating system level. But nowadays people, when they say containers, they mean different things, so we try to stop using the term containers. So this is light VMs. Light means that in these virtual machines, flexibility is sacrificed for the sake of performance. Our light VMs are denser and faster than KVM/QEMU virtual machines. Our main customers are hosting providers, so the main Virtuozzo usage is supporting virtual dedicated hosting, inside which the typical software that is run are web services. And this is what we see constantly, and this is what we implicitly optimize Virtuozzo performance for. So this talk actually is not about Virtuozzo itself. This talk is mostly about lessons we've learned when running popular web services in NGINX in particular in the public cloud. What we've seen so far and what performance improvements we've made. Having said that, this talk is not about why someone should launch NGINX only in Virtuozzo light VMs. Of course, it's not a generic solution to everyone's problem, but if you want to do it, my advice would probably be very useful. When running web services in our customers' environment, we see some special things. So first of all is that we do not see extremely high load on the networking. Typically networking bandwidth itself is enough for what hosting providers customers see, but what they do want is low networking latency. And since we can do nothing with hardware NICs, but we use virtual NICs to pass traffic between host and virtual environments, we of course can do something with virtual NICs. Next thing that we constantly work with is memory overcommitment. Hosting providers tend to oversell resources to their clients, so when they run light VMs, the amount of memory all of them might request from the system will definitely exceed the amount of RAM on the host. Next thing that is typical for hosting providers environment, which is partially a consequence of the previous constraint, is active use of on-disk data and metadata. In modern content management systems, like WordPress, for example, there is a lot of small files with configurations, images, CSS templates, whatever, and each request typically results in bringing up lots of this data from disk or from in-memory cache. And also, what we see, it's somewhat special to Virtuozzo, is lots and lots of cloned containers. When hosting providers sells a dedicated virtual environment to its clients, it typically creates them from some template. So what we see is hundreds and thousands of light VMs running on a host which effectively contain a lot of identical data. So to handle all of this, we mainly concentrate in the performance terms on three directions. First of all is IPVLAN-like networking device. Second thing is advanced memory management. And active page cache deduplication. So let's proceed to each of them in a little bit more details than just summaries. So Virtuozzo networking. As I said, it's an IP-VLAN virtual net device. What this means, in classical VM environments, which is shown on the left, virtual machines are connected to the networking using so-called virtual Ethernet device and bridge. So what you will see in your VM setup if you use KVM is virtual Ethernet adapter on both sides, on VM side and on the host side. And from the host side, the virtual adapter is bridged with the host real adapter. Sometimes instead of real Ethernet hardware, people use bonding devices or VLAN devices, but it doesn't change much. Anyway, bridging and virtual Ethernet is used. In Virtuozzo, we do not need such complexity. Instead, we create an IP VLAN group. If you know how classical VLAN works, they extend the headers of the packets, put in additional VLAN tag inside, and upon arrival of a packet onto host network adapter, they look at this tag and decide to which virtual adapter to quickly forward the packet. We do effectively the same, but without a VLAN tag. Instead, we're looking at the destination IP address and forward the packet to one of virtual, we call them VNet devices, instead of putting the packet into bridge and letting it make the decision of where to forward the packet. With that approach, we can see lower latencies in transmitting the packets, purely because there are less CPU instructions that virtual NIC driver does to deliver a packet from host NIC to the transport layer, to the TCP socket of the container, to the light VM, sorry. This IP VLAN device uses a little bit less memory than even virtual Ethernet adapter, which exists for containers in the Linux kernel, but it's not that big. It's just a pleasant surprise we've got from using IP VLAN device. And the third thing is not about performance, but about security. With VNet device, it's impossible from inside the light VM to do MAC spoofing. So the IP address hosting provider has assigned to his client is guaranteed to remain such. There is no way to change this and fake ARP requests or do tricks like that. When it comes to numbers, sorry for the small font, the blue bars are VNet device and red or orange, how you see them, bars are virtual Ethernet device bridged with the host. Measuring TCP latency and UDP latency on thousands of connections, we see that VNet works several % faster than virtual Ethernet device. However, networking latency is not the biggest gain in Virtuozzo. Virtuozzo memory management, it might give you much better performance gain than just using VNet device. So nowadays, I would say it's already traditionally, the memory management when running multi-tenant applications using, for example, Docker or LXC or even KVM would be to use already native Linux kernel memory control groups, which has been implemented years ago. It has been improved significantly since then, but still default upstream memory control group uses hard limits to manage the memory inside these virtual domains or virtual containers. There is a notion of so-called soft limit inside control groups, but this notion is not stable in terms of API. It has been changed 3 or 4 times already, so the only stable way to limit your virtual entity with some memory is to configuring hard limits, and this hard limit is really hard. There is no way for a container to bypass this limit. The second thing inside default C groups is that when we're out of memory, which happens constantly in overcommitted environments, kernel does proportional reclaim of pages from each of the C groups, thus draining memory from all the containers that are launched on the host. And this is done so because of it's an upstream code in the mainstream Linux kernel, and for different narrow use cases, it's hard to persuade the whole community that we need to fix the reclaim algorithm this way or another. So they stick to use the most simple one, which suits mostly all the parties, or not suits them all at the same level. And the third problem with memory C group is that there is no chance to quickly tune the reclaim policy once you have the kernel up and running on the host. Because, as I said, it's a kernel code, and in order to fix that, you have to patch the kernel, get the code upstream, recompile it, and reboot the host. That's way too complex. To fix that, and fixing this turned out to be important, as I will show in the end of my talk with a performance slide. To fix this, we implemented a user space monitor called VCMMD, which improves the reclaim policy of the memory control group. It improves only reclaim policy because when you have enough memory to host, to serve all your needs, there is nothing to improve there. All data sits in memory. It's the fastest way of operation. So the most interesting part of this game is when we are out of memory and have to reclaim some pages from some virtual environments, or from light VMs in our case. So what virtual memory manager does is it implements programmable reclaim policies. It uses existing memory control group interface and some other kernel interfaces and facilities to control the way how kernel reclaims data. It helps kernel better keep unused memory really in memory if there is still space for that, so it doesn't hurry up throwing the pages from the memory. By using this, it better handles quick, short spikes in memory consumption, because this is what happens quite often. Memory consumption is not that big, but sometimes some virtual environment needs more memory for a short period of time. So this virtual daemon tracks that. It helps memory C group reuse host memory when it uses, when it's available. And the third feature of this daemon is that it really helps memory control group to reclaim memory which has been unused for a very long time. It's typical for a lot of applications that they can bring up some memory into the system, put some data into it, and actually stop using it forever. In classical and traditional memory C group, this memory will sit in the memory forever unless virtual environment hits the hard limit. But with the Virtuozzo memory daemon, this memory will be reclaimed, and other virtual environments will be allowed to use this. And the third thing that we improved in Linux kernel and classical Linux kernel is disk deduplication. So as I told, we see a lot of cloned containers on the hosts, and what we want is to make the identical files not populate the memory cache with copies of each other. There are actually two ways to keep virtual machine or our container files on disk. First is just to put files directly on the host file system and limit the file system view of a container with some subtree by calling change root system call. When putting all containers files on the same file system, we have better packed on disk data because a single file system decides how to allocate blocks and put the files much better when it sees the whole picture. We can change the limits on how much of disk each light VM can use very easy because it's just a counter in the kernel. We change it and container can no longer grow its own disk data. And putting files on a single FS could allow us to effectively share files between light VMs. This is what done by default in Docker. It puts files in layers and then joins them using the overlay FS file system. But there is the second way to put container files on disk, which we use in Virtuozzo. It's by creating a virtual block device, putting a file system into block device, and then letting light virtual machine work on that block device. With the second approach, we lose all the benefits of FS-based approach, but instead we have better per light VM disk quota. We get an ability to live migrate light virtual machines, and this is quite a tempting feature of Virtuozzo customers. We solve a problem of journaled file systems when a journal becomes a bottleneck if you start many containers in file system-based setup. And putting files into virtual block device gives much better management and performance results when it comes to distributed storage. Nowadays, there is no distributed file system which really works as a file system. Ceph exists, of course, but its performance when it works in the file system mode is really bad. It works much better in so-called RBD mode, which is effectively a virtual block device. So in Virtuozzo we use block device, but with block device we by default lose the ability to merge files together because disk cache in Linux works this way. If it sees two different block devices, it just creates two copies of the memory cache for this. So to fix this, we have implemented a technology called PF cache. It is partially in the kernel, partially in the user space. It's effectively a modification to ext4 and to ext4 file system and to Linux disk cache subsystem that helps identical files to share page cache pages. The result is twofold. First of all, we reduce the memory consumption because disk cache is not duplicated. But which is more important, we do not duplicate the disk I/O. When it comes to reading identical files from disk, file is read only once. All the other containers that need the same file from their block devices, they get already existing page from the page cache. Combining the two last technologies I've described, the memory manager and active disk deduplication, we can see a great performance improvement. So here is the result of testing the response time of a place control panel, which has NGINX running in front of it as a as cache, which serves static content and serves big number of connections. So we increase the amount of virtual environments on the host, and at the same time increase the amount of clients that generate requests to the panels. Up to some point in time, when the whole workload fits into the server memory, all three setups, they come at the same rate. And the setups are, blue line is when all the optimizations are turned off, so no deduplication and default memory control group is used. Red line is when PF cache is turned on and it deduplicates disk cache in memory, and the yellow line is when we turn on the memory manager daemon, which helps to reclaim memory. So first interesting point is when the blue line goes down, it means that the system has run out of memory. And the first aid to this is to pack memory cache, disk cache better, so that the workload still sits in the memory. So yellow and red lines go up. The second point is when the red line goes down. This is when even deduplication stops helping and system starts reclaiming the memory. If the memory management daemon doesn't help memory control group, kernel starts reclaiming pages in not very effective manner, and the request rate falls down. The yellow line still goes on a good enough level, showing that things that we've done in the VCMMD really help. So this is it. If you have any questions, you can ask them now. All right, thanks for coming.